Look up on a clear night, and you might see it. A faint smudge of light in the constellation Andromeda. It looks small, unremarkable, easy to miss. But that tiny glow is hiding something extraordinary. That gentle patch of light is actually a galaxy containing 1 trillion stars, stretching so far that if you could see its full extent, it would appear 6 times wider than the full moon. Andromeda is not small. We've just been looking at the wrong parts. Tonight, as you rest, we're going to explore how Andromeda kept growing larger the more we looked at it. How every improvement in our telescopes revealed that we'd been seeing only a fraction of what was really there. How what seemed like a modest neighbor turned out to be one of the most expansive structures in our corner of the universe. Welcome to Cosmic Sleep Stories. If you enjoy these quiet journeys through cosmic mysteries, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, all you need to do is rest. Let your eyes close. Allow your body to sink into comfort. And let your mind drift gently outward, toward a galaxy that refused to stay inside the boundaries we drew for it. Let's begin. There is a quiet brightness beyond the familiar stars of our sky. Nothing dramatic, nothing insistent, and yet it extends outward on a scale that challenges comprehension. For most of history, Andromeda was thought to be a cloud, a distant smudge of unresolved light, quietly fixed in place among the stars. Its apparent size seemed modest. Its boundaries appeared gentle and contained. Nothing about it suggested enormity. Modern astronomy has learned to be wary of appearances. As telescopes became more sensitive and observations more patient, Andromeda began to reveal layers that had never been seen before. Long exposures uncovered stars far beyond its bright spiral arms. Wide-field surveys traced faint stellar streams stretching outward like echoes of ancient motion. Measurements of how stars and smaller galaxies move around it hinted at mass extending far past anything that shines. With each improvement in observation, Andromeda seemed to grow. Not suddenly and not dramatically, but quietly. Its edges softened. Its outline blurred. What once looked like a neatly bounded island of stars became something far more diffuse, more expansive, and harder to define. As you drift now, let yourself appreciate how often this happens in science. What we think we know becomes just the beginning of what there is to discover. Andromeda looked small because we could only see its brightest parts. The rest was there all along, patient, waiting for us to develop eyes sensitive enough to notice. Astronomers discovered that asking how big Andromeda is depends on what is being measured. The luminous disk that first caught the eye? The vast halo of ancient stars surrounding it? Or the invisible structure inferred through gravity alone? Each tells a different part of the story, and each expands the galaxy well beyond its familiar appearance. Some of the most significant discoveries came almost unintentionally. Surveys designed to study nearby stars kept finding Andromeda stars where none were expected. Projects meant to refine distances instead revealed structures hundreds of thousands of light-years across. Even the space between Andromeda and the Milky Way turned out to be less empty than once believed, threaded with overlapping regions that challenged the idea of where one galaxy ends and another begins. Over time, the question shifted. It became less about locating a clear edge and more about understanding influence. How far Andromeda's stars extend. How far its gravity reaches. How much space is quietly shaped by its presence. This is not a story with a single number waiting at the end. It is a slow unfolding of perspective, shaped by decades of observation and refinement. Let that settle gently as you rest. The universe doesn't offer neat answers. It offers layers of understanding, each one deeper than the last. And sometimes the most profound discoveries come from realizing that what we thought was complete was actually just the beginning. At the beginning of the 20th century, Andromeda did not yet feel enormous. It did not even feel like a galaxy. Through the telescopes of the time, it appeared as a soft, elongated glow, a misty patch of light stretched gently across the sky, brighter in the center and fading outward into darkness. Astronomers referred to it as the Andromeda Nebula, grouping it with other cloudy objects whose true nature was still unclear. Some thought these nebulae were nearby collections of gas and dust-forming stars within the Milky Way itself. Others suspected they might be something far larger. But there was no way to be sure. The problem was not imagination. It was measurement. Early telescopes were limited by glass quality, atmospheric distortion, and the sensitivity of the human eye. Even when photography began to assist astronomy, the earliest photographic plates could capture only the brightest regions of an object. Anything faint, diffuse, or spread thin across the sky simply failed to register. Darkness swallowed it whole. So when astronomers pointed their instruments toward Andromeda, what they recorded was only its most obvious feature. A bright central region, a smooth glowing core, a disk that seemed well-defined and comfortably contained. The outer reaches, where light thins and stars grow sparse, remained invisible. As sleep deepens, let yourself appreciate how much we miss when we can only see the brightest parts of things. This is true not just in astronomy, but in life. The most important aspects are often subtle, requiring patience and attention to perceive. Andromeda was teaching us this lesson even before we knew it was a galaxy. To early observers, Andromeda looked modest. Larger than most nebulae perhaps, but still something that could plausibly fit inside the Milky Way. Its apparent size on the sky was measured in angular terms, how wide it appeared compared to familiar reference points. By those measures, it seemed manageable, finite, knowable. That impression shaped early estimates. Photographic plates taken in the late 19th and early 20th centuries captured Andromeda as a flattened oval of light. Astronomers traced its visible outline and assumed that what they could see represented most of what existed. This was a reasonable assumption at the time. After all, if something emitted light and that light did not appear on the plate, how could it be there? The answer, it turned out, was patience. Photographic plates required long exposures, sometimes nights, to collect enough light to form a clear image. Even then, they struggled with faint stars and low surface brightness regions. The human eye peering through an eyepiece fared no better. Vision adapts poorly to subtle gradients. Where light fades gradually, the brain often decides that nothing is there at all. As a result, Andromeda's bright core dominated attention. The outer regions were assumed to taper off quickly. Its size was underestimated not because astronomers were careless, but because the universe was quieter than their instruments could hear. Let that be comforting as you drift. Being wrong is not failure. It's the natural result of working with limited tools. Every generation sees more than the last, not because they're smarter, but because technology improves. We're always working at the edge of what's possible, doing the best we can with what we have. The question of what Andromeda truly was came to a turning point in the early 1920s. Careful observations of individual stars within the glowing patch revealed something extraordinary. Some of those stars changed brightness in a predictable way, allowing their intrinsic luminosity to be estimated. Comparing that intrinsic brightness to how faint they appeared revealed their distance. The numbers were unsettling. Those stars were far too distant to belong to the Milky Way. They lay well beyond its boundaries, separated by distances that forced a dramatic rethinking. Andromeda was not a nearby cloud. It was an entire galaxy, comparable in scale to the Milky Way itself, containing countless stars of its own. With that realization, Andromeda suddenly grew. Not physically, of course, but conceptually. It was no longer a small structure tucked inside our home galaxy. It was a separate island of stars adrift in the vastness between galaxies. Even so, its size was still underestimated. Knowing that Andromeda was a galaxy did not immediately reveal how large that galaxy truly was. The same observational limitations remained. Telescopes still captured mostly the bright inner disk. Photographic plates still missed faint outskirts. Astronomers now understood that Andromeda was vast, but they still did not know just how far it extended. As you rest now, appreciate how understanding comes in layers. First we learned Andromeda existed. Then we learned it was a cloud. Then we learned it was a galaxy. Each step felt complete at the time. Each was actually just preparation for the next discovery. Early size estimates focused on the luminous region, the spiral structure where stars were densely packed and easily visible. This region appeared well-defined, with graceful arms curving outward from the center. Beyond those arms, the light seemed to drop away. It was natural to assume that the galaxy ended not far beyond that point. This assumption shaped diagrams, textbooks, and mental images for decades. In reality, those early measurements were like judging a city by its downtown alone. Bright, crowded, and easy to see, but hardly representative of everything that lies beyond. The suburbs, the outskirts, the quiet regions where lights are sparse and distances stretch out, were missing entirely from the picture. The limitations of early instruments meant that Andromeda's faint stars blended into the background glow of the sky. The universe itself is not truly dark. Air glow, scattered light, and the combined shimmer of countless distant stars create a soft background that hides delicate structures. Against that glow, Andromeda's outer regions simply vanished. There was also a psychological element at work. Human perception prefers edges. It looks for boundaries and clean shapes. When a glow fades gradually rather than stopping abruptly, the mind often interprets the fading as an ending. Early astronomers, like all observers, were influenced by this tendency. Where the image became indistinct, they assumed the object had finished. So Andromeda was drawn smaller than it truly was. This underestimation persisted well into the middle of the 20th century. Even as telescopes improved, the focus often remained on the brightest, most photogenic parts of the galaxy. Yet the seeds of revision had been planted. Astronomers now knew that appearances could deceive. They knew that galaxies were not neat, compact objects, but sprawling systems shaped by gravity over immense spans of time. The realization that Andromeda was a galaxy opened the door to a deeper question, one that would take decades to unfold. If the bright disk was not the whole story, how much lay beyond it? When telescopes left the surface of Earth, Andromeda changed again. Not because the galaxy itself altered in any way, but because the view finally did. For centuries, every observation of the sky had been filtered through the same restless layer of air. Earth's atmosphere bends incoming light, scatters it, and adds a faint glow of its own. Stars shimmer, edges soften, fine detail slips away. Space-based observatories removed that problem in one decisive step. By orbiting above the atmosphere, they allowed light from distant objects to arrive undisturbed. What reached the detector was cleaner, steadier, and far more precise. When instruments like the Hubble Space Telescope turned toward Andromeda, the galaxy did not suddenly become brighter. It became clearer. One of the most important differences was time. Hubble was designed to stare. Instead of capturing a quick glance, it could remain fixed on the same region of sky for hours or days, collecting faint light bit by bit. Each photon that arrived was recorded and added to the rest. What could not be seen in a short exposure slowly emerged in a long one. This change alone reshaped Andromeda's appearance. Earlier images had shown a bright spiral disk, well-defined and elegant, fading neatly into darkness. Hubble's longer exposures began to reveal stars scattered beyond that familiar outline. At first, they appeared as isolated points, almost accidental. Then, as exposure times increased, they formed patterns, streams, halos, extensions that could not be ignored. The visible disk expanded. Not abruptly, not dramatically. It stretched outward quietly, the way dawn light spreads before sunrise. Each deeper image pushed the boundary a little farther, revealing that what once looked like empty space was in fact thinly populated territory. As you drift deeper, let yourself feel the patience that discovery requires. Nothing dramatic happened. No sudden revelation. Just longer exposures, more sensitive detectors, the willingness to look at what seemed like nothing and wait long enough for something to appear. This process highlighted something fundamental about how telescopes work. They do not show objects as they are in some absolute sense. They show what light allows them to show, given enough time and sensitivity. Bright regions dominate quickly. Faint regions require patience. Andromeda's outer stars are faint not because they are unusual, but because they are spread across enormous distances. Their light is real, but diluted against the soft background glow of the universe. Hubble was especially well suited to this task. Its sharp vision allowed astronomers to distinguish individual stars in Andromeda rather than seeing only a smooth haze. By counting these stars and measuring how their density changed with distance from the center, astronomers could trace the galaxy far beyond its previously accepted edge. What they found was not a wall. It was a gradient. Star density declined gradually as distance increased. There was no sudden cutoff, no clear line where the galaxy stopped and space began. Instead, the light thinned, softened, and slowly blended into the background. This realization changed how astronomers talked about size. If a galaxy fades rather than ends, then its apparent size depends on how faint a glow the telescope can detect. A more sensitive instrument sees farther. A longer exposure reveals more. The boundary is not fixed. It moves with technology. Let that settle as sleep approaches. Galaxies don't have edges the way countries do. They fade. They thin. They dissolve gradually into the space around them. And that means how big is always a question with multiple answers, depending on how deep you're willing to look. Even with Hubble, that boundary remained provisional. As powerful as it was, Hubble still had limits. Beyond a certain point, Andromeda's stars became too sparse and too faint to separate cleanly from the background of distant galaxies and cosmic light. Noise began to compete with signal. This meant that even Hubble could not see the galaxy in its entirety. That fact is easy to overlook when looking at its images. They feel complete, expansive, satisfying. But astronomers working with the data were always aware that what they were seeing was a lower limit, not a final outline. The galaxy was at least this large, possibly larger. The next shift came when astronomers decided to stop focusing on the center and instead map the space around it. Wide-field surveys changed the question entirely. Rather than asking what Andromeda looks like, they asked where its stars actually are. One of the most influential of these efforts was designed not to take a single beautiful image, but to systematically scan a vast region of sky surrounding the galaxy. The goal was deceptively simple. Identify individual stars that belong to Andromeda, even far from its bright core, and see how far outward they extend. To do that, astronomers relied on a particular kind of star: red giants. Red giant stars are especially useful because they are luminous and relatively easy to identify, even at great distances. Their brightness and color follow predictable patterns, making them reliable markers of membership. When astronomers began plotting the positions of these stars across wide swaths of sky, something unexpected emerged. They kept finding them far beyond where the disk was supposed to end. At first, these detections were sparse. A few stars here, a few there. It would have been easy to dismiss them as outliers or background confusion. But as the survey expanded and the data accumulated, patterns began to appear. The stars were not random. They formed a diffuse, extended structure surrounding the galaxy. Andromeda had a halo. This stellar halo was not a thin shell or a neat boundary. It was a vast, roughly spherical distribution of ancient stars stretching far beyond the luminous spiral arms. In some directions, red giant stars associated with Andromeda were detected hundreds of thousands of light years from the center. This alone changed everything. Earlier estimates had focused almost entirely on the visible disk, which spans on the order of a few 100,000 light years across. The discovery of the stellar halo effectively doubled that scale. Andromeda was no longer just a spiral galaxy with elegant arms. It was embedded within a much larger, more diffuse structure. As you rest now, appreciate how the most expansive parts of things are often the quietest. The halo doesn't dominate images. It doesn't capture attention. It requires patience, careful measurement, and a willingness to look where nothing obvious appears. And yet it's real, vast, ancient, carrying the history of the galaxy and its faint stars. Importantly, this was not a sudden announcement or a single dramatic paper. It was a gradual realization that unfolded as more of the survey was completed. Each new patch of sky added more points. Each confirmation strengthened the picture. The galaxy did not grow overnight. Understanding did. There was a quiet elegance to this process. Astronomers were not redefining Andromeda based on speculation or theory alone. They were counting stars, mapping positions, comparing densities. Where the number of red giants declined slowly rather than abruptly, the halo persisted. Once again, there was no sharp edge. The halo faded gradually, just as the disk had, but on a far larger scale. Its stars were old, often older than those in the spiral arms, relics of Andromeda's early history. Some likely formed in the galaxy itself. Others may have been acquired long ago, pulled in from smaller galaxies, and stretched into long streams by gravity. These streams were another clue. Wide-field surveys revealed faint, elongated structures wrapping around Andromeda, the remnants of past mergers. They traced graceful arcs across the halo, evidence that the galaxy had grown not only by forming stars, but by absorbing others over billions of years. Each merger added stars to the outskirts, extending the galaxy's reach. This made the concept of size even more slippery. Was Andromeda as large as its disk, as its halo, or as far as its oldest, most loosely bound stars could be found? The answer depended on perspective, but one thing was clear. Earlier measurements had been missing a significant fraction of the galaxy. The stellar halo revealed just how much had been hidden in plain sight. Its stars were not invisible. They were simply too subtle for earlier instruments and too spread out for narrow observations. Once astronomers widened their field of view and focused on individual stellar traces, the galaxy's true scale became impossible to ignore. For a long time, Andromeda's spiral disk felt like the whole story. It is the part of the galaxy that announces itself most clearly. Bright, structured, elegant. From even modest telescopes, the disk reveals sweeping spiral arms wrapped around a luminous central bulge. Dust lanes cut dark curves through starlight. Star-forming regions glow softly, marking places where gas is dense and active. It looks complete, almost self-contained, as if the galaxy has been neatly drawn and carefully finished. It is easy to see why astronomers once thought this was essentially all of Andromeda. The disk is visually striking because it concentrates light. Stars are packed closely enough that their combined glow stands out clearly against the sky. Early measurements naturally focused here. Astronomers traced the visible spiral arms and measured how wide they appeared. They mapped the bright regions where stars were easiest to count. Over time, these measurements became more precise, and disk size estimates began to settle into a consistent range. Unlike the halo, whose boundaries kept expanding as instruments improved, the disk seemed stable. It did not keep growing. This stability gave the disk an air of authority. If something was measurable, repeatable, and visually obvious, it felt reliable. But even as the disk's size stabilized, something curious was happening within it. Astronomers began measuring how gas moves inside Andromeda. Clouds of hydrogen gas emit radiation at specific wavelengths that radio telescopes can detect, even when the gas itself is invisible to optical telescopes. By observing how this emission shifts as different parts of the disk move toward or away from Earth, astronomers could measure rotation. This produced what are known as rotation curves, showing how fast different parts of a galaxy orbit its center at different distances. If most of a galaxy's mass were concentrated in the bright disk, then stars and gas farther out should orbit more slowly. Much like planets in the outer solar system move more gently around the sun. That is not what Andromeda showed. Measurements revealed that gas far from the center was moving faster than expected. Instead of slowing down, orbital speed stayed roughly constant across much of the disk. This told astronomers that the mass influencing motion extended well beyond the bright regions they could see. The disk was orderly, but it was not telling the whole truth. Let that mystery settle as you drift. The visible parts of Andromeda, the parts that look complete and satisfying, were actually just hints of something much larger. The real mass, the real extent, lay hidden in darkness, and it would take different kinds of observation to reveal it. At first, the stars appeared where no stars were supposed to be. They showed up quietly at the limits of deep observations, scattered far beyond Andromeda's bright spiral disk. Individually, they were unremarkable, old, dim, easy to overlook. But taken together, they began to tell a story that reshaped how astronomers understood the galaxy. These stars belong to Andromeda's stellar halo. The halo is not a structure that announces itself. It does not shine brightly or form graceful patterns. It is diffuse, extended, and sparse, made up of stars spread across enormous distances. Deep star counts changed everything. By carefully counting individual stars across wide areas of sky, astronomers were able to trace Andromeda's population far beyond the visible disk. Red giant stars again played a key role. Their predictable brightness allowed researchers to identify them reliably, even when they were scattered thinly across space. As these surveys expanded, the scale of the halo became impossible to ignore. Halo stars associated with Andromeda were found at distances exceeding 600,000 light-years from the galaxy's center. In some directions, they stretched even farther, dissolving gradually into the surrounding space. This was not a narrow shell or a tidy boundary. It was an enormous extended envelope of stars surrounding the galaxy like a faint mist. This discovery alone transformed earlier size estimates. If Andromeda's disk had once defined its scale, the halo redefined it entirely. The galaxy was no longer measured only by where its light was brightest, but by where its stars still belonged gravitationally. Including the halo effectively doubled the galaxy's known extent. And this was not speculation. These stars were not random background objects. Their distances, motions, and properties matched what would be expected of Andromeda's population. As sleep deepens, let yourself appreciate the patience this required. Counting faint stars across vast regions of sky, confirming each one, building up a picture star by star. Nothing dramatic, just careful, methodical work revealing that Andromeda was far larger than anyone had imagined. One of the most revealing clues came from metallicity. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium within a star. Stars formed early in the universe tend to have low metallicity because heavier elements had not yet been widely produced by generations of stellar evolution. When astronomers measured the metallicity of Andromeda's halo stars, a clear pattern emerged. These stars were old, very old. Many had formed early in the galaxy's history, long before the spiral disk took on its present form. Some of these stars likely formed within Andromeda itself during its earlier stages. Others were probably acquired later, pulled in from smaller galaxies that wandered too close and were gradually torn apart. Their remains were stretched into long, faint streams that now laced the halo. The halo, it turned out, was a record of Andromeda's past. Every faint star carried information about how the galaxy grew. Each stream marked a merger long completed. Each metallicity measurement added a piece to the timeline. As surveys pushed farther outward, another subtle realization followed. Andromeda's halo does not exist in isolation. The Milky Way has a halo of its own, similarly extended and similarly diffuse. And when astronomers mapped the outskirts of both galaxies, they found that these halos overlap. The space between Andromeda and the Milky Way is not empty. It is shared. This overlap does not mean the galaxies are colliding in a dramatic sense. It means their gravitational influence extends so far that their outermost stars occupy the same broad region of space. The boundary between them is not a line, but a transition. Rest in that image as you drift. Two galaxies so large that their edges blend together. The space between them not empty but shared, threaded with ancient stars that belong to both and neither, moving slowly through a region shaped by the gravity of two massive systems. This was a quiet but profound shift in thinking. Galaxies were no longer separate islands surrounded by emptiness. They were expansive systems whose outskirts blended together. Their influence reached far beyond their bright centers, overlapping gently with their neighbors. Brightness once again proved to be a poor guide. The stellar halo is faint precisely because its stars are spread so widely. Their combined light is thin, diluted across vast volumes of space. To the eye, and even to many telescopes, this looks like nothing at all. But the stars are there, moving slowly, bound by gravity, tracing out the true scale of the galaxy. This realization forced astronomers to rethink the idea of an edge. If a galaxy fades gradually rather than stopping, then its edge is not a place. It is a concept, a region where membership becomes ambiguous, where stars are few and where definitions grow soft. Andromeda does not end where brightness ends. It continues quietly outward, patient and vast, and impossible to draw a line around. For a while, Andromeda's size was discussed almost entirely in terms of light. How far the disk extended, how faint the halo became, where stars could still be seen. But light, it turned out, was only part of the story. As astronomers began to focus on how things move inside and around Andromeda, the meaning of size shifted in a fundamental way. Motion carries information that light alone cannot. It reveals where mass is, not just where stars happen to shine. The simplest idea is intuitive. Objects move faster when more mass is pulling on them. Measure how fast something moves, and you can infer how much mass must be present to keep it on course. Inside Andromeda, this approach began with stars and gas. Astronomers tracked how quickly material orbited the galaxy's center at different distances. These measurements had already hinted that the visible disk did not contain all the mass influencing motion. Orbital speed stayed high even where starlight thinned. But the most striking clues came from much farther out. Andromeda is surrounded by smaller satellite galaxies, each bound loosely by gravity. These companions move slowly, tracing wide, elongated paths through space. By measuring their velocities and trajectories, astronomers could estimate how much mass Andromeda must contain to keep these satellites from drifting away. The answer was unsettling. The visible stars accounted for only a fraction of the required mass. Even when the disk and stellar halo were included, there was still far too little matter to explain the observed motions. Something else was contributing. Something extended. Something invisible. Let that settle gently as you drift toward sleep. Most of Andromeda's mass doesn't shine. Can't be photographed. Can't be seen at all. It's only felt through gravity, through how it shapes the motion of everything around it. This is where dark matter entered the story, not as an exotic idea, but as a practical necessity. Astronomers were not searching for mystery. They were trying to make sense of motion. And motion demanded more mass than light could provide. Dark matter does not emit light. It does not absorb it. It does not glow, sparkle, or cast shadows. Its presence is inferred entirely through gravity, through how stars move, through how gas rotates, through how satellites remain attached to their host galaxies. In Andromeda, the dark matter halo dominates the galaxy's mass. This halo is not a thin shell or a compact structure. It is an enormous, roughly spherical distribution extending far beyond the visible galaxy. Estimates suggest that Andromeda's dark matter halo likely reaches out over 2 million light-years in diameter, perhaps more. This means that the galaxy's gravitational influence stretches far beyond where any stars can be seen or even reliably counted. Most of Andromeda is invisible. The bright spiral disk is just the tip. The stellar halo is just a trace. The real mass, the real extent, lies in darkness. And yet this darkness is not empty. It's filled with something. We don't know what. We can't see it directly. But we know it's there because nothing else can explain how Andromeda holds together, how its satellites orbit, how its influence extends so far. As sleep deepens, rest in that mystery. The universe is mostly made of things we can't see. Dark matter, dark energy, the invisible framework that holds everything together. And somehow that's okay. We can study it through its effects. We can map it through motion. We can understand it even though we can't photograph it. Importantly, dark matter halos don't have sharp edges. They fade gradually, just like everything else. At great distances from Andromeda, the dark matter density decreases. The gravitational influence weakens. Eventually, it becomes impossible to say where Andromeda's halo ends and the general cosmic background begins. This is especially true in the space between Andromeda and the Milky Way. Both galaxies have dark matter halos. Both extend far beyond their visible forms. And in the region between them, these halos overlap. The space is shaped by both galaxies at once. Neither dominates completely. This means that asking where Andromeda ends becomes genuinely difficult. Not because we lack data, but because galaxies themselves don't have clear boundaries. They fade. They overlap. They blend into each other and into the larger structure of the universe. So when we ask how big Andromeda is, the most honest answer includes all of this. The disk, a few 100,000 light-years across. The stellar halo, extending perhaps 600,000 light-years or more. And the dark matter halo, reaching potentially over 2 million light-years, maybe farther, fading gradually until it's impossible to distinguish from the background. That's not a failure of measurement. That's what galaxies are actually like. Extended, diffuse, gradual. The bright parts we can see are just the beginning. The real scale is written in gravity. And now, as we drift toward the end of this journey, let yourself feel the appropriate scale of what Andromeda actually is. Not a neat spiral disk. Not a tidy object with clear boundaries. But an enormous, layered system. 1 trillion stars in the bright center. Ancient halo stars tracing the outskirts. And an invisible halo of dark matter extending so far that it blends with the Milky Way's own halo in the space between. All of this is Andromeda. All of it real. Most of it invisible. And all of it so vast that we've spent a century slowly realizing just how much we were missing. The galaxy that looked like a small cloud in early telescopes turned out to be one of the largest structures in our corner of the universe. Not because it grew, Because we finally learned how to see it properly, how to look past the obvious, how to trace faint stars, how to measure motion, how to infer mass from gravity. Each improvement in our ability to observe added another layer to our understanding. And each layer revealed that Andromeda was larger than we'd thought. The disk grew when we could detect fainter light. The halo appeared when we counted individual stars. The dark matter halo emerged when we measured how satellites move. And even now, we're probably not seeing everything. Future observations will likely reveal more. Fainter structures, more distant streams, better maps of the dark matter distribution. Andromeda will continue to grow in our understanding, not because it's changing, but because we keep getting better at looking. Let that be comforting as sleep approaches. We're always at the edge of our ability to see, always working with limited tools, always missing some of what's there. And that's okay. Understanding grows. Each generation sees more. Each improvement in technology reveals another layer. Andromeda taught us that size in astronomy is not a single number. It's a collection of measurements, each one valid, each one incomplete on its own. The disk is real. The halo is real. The dark matter is real. And they all coexist, creating a structure far more complex than any single measurement can capture. So how big is Andromeda really? It depends on what you're measuring and how deep you're willing to look. But in every sense that matters, it's vast. Larger than early astronomers imagined. Larger than most people realize when they glance at that faint smudge in the sky. Larger than its brightness suggests. It's 1 trillion stars spread across hundreds of thousands of light years. It's ancient halo stars tracing paths through space for billions of years. It's an invisible halo of dark matter extending millions of light years, shaping the motion of everything nearby. It's a galaxy that refused to fit inside the boundaries we drew for it, that kept revealing more every time we looked deeper, that taught us, gently and patiently, that the universe is always larger and stranger than we think. And now, finally, you can let all of this go. You don't need to remember the numbers. You don't need to hold on to the details. Just rest in the knowledge that out there, 2.5 million light years away, is a galaxy so vast it took us a century to even begin to comprehend its true size. Sleep well. Dream of galaxies fading into darkness, of halos extending farther than light can reach, of boundaries that dissolve rather than stop, of a universe patient enough to wait while we slowly learn to see what's been there all along. But before sleep takes you completely, let's explore a few more layers of Andromeda's story. Because the galaxy's size isn't just about its own stars. It's also about what orbits around it, what it has consumed, and what it will become. Andromeda is not alone. Scattered around it are smaller companion galaxies, satellites bound by gravity, moving slowly through space on paths that can take billions of years to complete. These satellites are like moons, but on a galactic scale. Each one is a galaxy in its own right, containing millions or billions of stars, yet dwarfed by Andromeda's mass. Astronomers have identified dozens of these satellite galaxies. Some are relatively close, orbiting within a few 100,000 light years. Others venture much farther out, following elongated paths that take them nearly 1 million light years from Andromeda's center before slowly curving back. The very existence of these distant satellites tells us something profound about Andromeda's reach. A satellite can only remain bound if Andromeda's gravity extends far enough to hold it. The fact that satellites orbit at such vast distances means the galaxy's gravitational influence must extend at least that far, and probably farther. Each satellite's motion provides clues. By measuring how fast it moves and how far it strays, astronomers can estimate how much mass lies within its orbit. And again, the same conclusion appears. Andromeda's influence extends far beyond what its visible stars would suggest. As you drift now, imagine these small galaxies moving through the darkness. Billions of stars in each one, yet they're just companions, satellites, minor players in Andromeda's gravitational theater. They trace enormous paths through space, patient witnesses to a galaxy's true extent. Some of these satellites won't survive. They're on collision courses with Andromeda, slowly falling inward. Over the next few billion years, they'll be torn apart by tidal forces, their stars scattered and absorbed into Andromeda's halo. This process is already happening to some of them. Which brings us to stellar streams. These are among the most beautiful and revealing features around Andromeda. Long, thin ribbons of stars stretching across hundreds of thousands of light years. They look like graceful arcs painted across the sky, sometimes looping elegantly, sometimes twisting in complex patterns. These streams are the ghosts of galaxies past. They mark the paths of smaller galaxies that wandered too close to Andromeda and were slowly pulled apart. The process is gentle, not violent. As a smaller galaxy falls into Andromeda's gravitational field, tidal forces begin to act. Stars on the near side feel a stronger pull than those on the far side. Over millions of years, this difference stretches the galaxy. Stars are peeled away, like taffy being pulled. They spread out along the orbit the doomed galaxy followed, creating a stream that traces its path. What remains is a stellar fossil, a record of an encounter that happened hundreds of millions or billions of years ago. Astronomers have mapped several of these streams around Andromeda. Each one tells a story. Each one extends the galaxy's observable reach farther into space. Because if stars from Andromeda's past meals are scattered this far out, then clearly the galaxy's influence extends at least this far. Let that image settle as sleep deepens. Streams of ancient stars, scattered remnants of galaxies that no longer exist, all held by Andromeda's gravity, all marking territory that belongs, in some sense, to the galaxy. The streams are faint, easy to miss, but they're part of Andromeda just as surely as the bright spiral arms. These streams also reveal Andromeda's history. The galaxy didn't start out this large. It grew. Over billions of years, it absorbed dozens, maybe hundreds of smaller galaxies. Each merger added mass. Each one extended the halo a bit farther. Each one left behind streams as evidence. This is how galaxies grow, not by forming new stars from nothing, but by cannibalism, by absorbing their neighbors, by slowly accumulating mass over cosmic timescales. Andromeda is larger today than it was a billion years ago. It will be larger a billion years from now than it is today. And this brings us to the future. What will Andromeda's size become? Astronomers use simulations to explore this question. By modeling how gravity works and how galaxies interact, they can project forward billions of years. What they find is a story of continued, gradual growth. Andromeda will keep absorbing its satellite galaxies. Each merger will add stars to the outskirts, extending the stellar halo. The dark matter halo will expand slightly as mass accumulates. The overall gravitational reach will increase. None of this will be dramatic. It will unfold over timescales so long that even a million years would show little change. But given enough time, the changes add up. Andromeda will continue becoming more extended, more diffuse, larger. Its bright spiral disk might remain roughly the same size, but the faint outer regions will stretch farther and farther into space. There's even a specific merger we know is coming. The Milky Way, our own galaxy, is on a collision course with Andromeda. In about 4.5 billion years, the two galaxies will begin to merge. Their dark matter halos are already overlapping. Over the next few billion years, they'll move closer. Eventually, their disks will interact. This won't be a collision in the everyday sense. Stars are so far apart that individual stellar collisions will be incredibly rare. Instead, the two galaxies will pass through each other, their gravitational interactions reshaping both. Over billions of years, they'll merge into a single, larger galaxy. When this merger is complete, the combined system will be even more massive than Andromeda is today. It will have a larger halo, more stars, greater gravitational reach. Astronomers have already given it a name, Milky, a blending of Milky Way and Andromeda, marking the end of both as separate galaxies and the beginning of something new. As you rest in this knowledge, appreciate the timescales involved. For 0.5 billion years from now, the Sun will be nearing the end of its life. Earth, if it still exists, will be uninhabitable, and two galaxies will be in the process of becoming one, adding another chapter to a story of growth that has been unfolding for over 10 billion years. Now let's consider what Andromeda would actually look like from the inside. Because all these measurements, all these vast distances, can feel abstract. What would it be like to exist within such an enormous structure? The surprising answer is spacious. Despite containing 1 trillion stars, Andromeda would not feel crowded. Stars are separated by enormous distances, typically several light years apart, even in the densest regions. In most of the galaxy, you could travel for years at the speed of light and pass nothing but darkness between one star and the next. This is one of the most common misconceptions about galaxies. They look dense because their light is compressed into images. Millions of stars projected onto a flat surface, stacked visually. But in three-dimensional space, those stars are spread across vast volumes. The galaxy feels more like a fog than a crowd. If you were inside Andromeda, most directions would appear dark. Stars would be points of light, not walls of glow. Even near the central regions where star density increases, the feeling would remain open and spacious. The average separation between stars would still be measured in tenths of a light year, not in closeness. Moving outward into the stellar halo, the sense of space becomes even more pronounced. Halo stars are sparse by design. You could drift for tens or hundreds of light years without encountering another star. The halo exists not because stars are numerous there, but because gravity holds them together across long distances. From within Andromeda, the galaxy's size would be felt not through density, but through extent. No matter which direction you looked, there would always be more space beyond the next star. The galaxy would feel boundless, not because it's filled, but because it's spread out. Let that spaciousness comfort you as sleep approaches. Even in something as massive as Andromeda, there's room. Vast amounts of room. The universe is not crowded. It's generous with space. There's also the question of how Andromeda compares to other galaxies. Is it unusually large, or typical for its type? When astronomers compare Andromeda to other spiral galaxies across the universe, using the same measurement techniques, a clear picture emerges. It's large, but not unusual. Many spiral galaxies are smaller, with compact disks and modest halos. Others are larger, extending farther and containing even more stars. Andromeda sits toward the upper end of the distribution, but not at the extreme edge. Its disk is broader than average, but not exceptional. Its stellar halo is extensive, but comparable to other large spirals. This context matters. Without comparison, Andromeda's size can feel overwhelming. With it, the galaxy becomes familiar. A large example of a common pattern rather than a singular outlier. What feels extraordinary is not Andromeda specifically, but the category it belongs to. Spiral galaxies themselves are enormous. The Milky Way shares this scale. So do many others scattered throughout the universe. Andromeda feels special because it's close, because we can study it in detail, because it dominates our local region of space. But cosmically, it's one of many massive spirals, each shaped by similar processes of growth and merger. There's something reassuring in this. The galaxy that once seemed to stretch endlessly outward turns out to be a well-behaved member of a larger population. Its vastness doesn't require special explanation. It emerges naturally from the same processes that shape countless other spirals. And now, as we drift toward final sleep, let's hold one more perspective. Every measurement of Andromeda describes the galaxy as it was over 2 million years ago. That's how long light takes to travel from Andromeda to Earth. When you look at Andromeda tonight, you're seeing it as it existed long before modern humans evolved. This means we're always looking into the past. The disk, the halo, the streams, the satellites, all are seen as they were, not as they are now. The galaxy may have changed since then, subtly, slowly, but meaningfully. On human timescales, 2 million years feels impossibly long. On galactic timescales, it's a brief pause. In that time, Andromeda has not transformed dramatically. Stars take hundreds of millions to billions of years to complete orbits. Galaxies grow through mergers that unfold over enormous spans of time. But the galaxy has not stood still either. Some satellites have moved closer. Some streams have stretched farther. Some stars have drifted outward into the halo. Astronomers account for this using simulations. They model how galaxies evolve, incorporating mergers, star formation, and the slow redistribution of matter. When simulations are matched to Andromeda's observed appearance, they suggest a gentle trajectory of growth. The galaxy is expected to continue expanding its halo gradually as it absorbs small companions. None of this is abrupt. The simulations indicate that Andromeda's overall size changes slowly, measured in hundreds of millions of years. Over the 2 million years represented by the light now arriving, the galaxy would have changed only slightly. Enough to matter scientifically, but not enough to invalidate observation. This time delay introduces a kind of humility. We're not measuring Andromeda as it is right now. We're measuring it as it was. The present-day galaxy exists just beyond direct observation, inferred rather than seen. But that's okay. That's astronomy. The universe doesn't offer real-time updates. It communicates through delayed signals, and we learn to interpret them with care. There's even beauty in this limitation. It reminds us that the universe is not rushing. Galaxies evolve slowly. Changes unfold over timescales that dwarf human experience. Even looking millions of years into the past, the picture remains broadly accurate. Andromeda's size is stable on timescales far longer than civilizations. So when we ask how big Andromeda is, we're really asking, how big was Andromeda 2 million years ago? And the answer, we now know, is vast. The disk spans hundreds of thousands of light years. The stellar halo extends perhaps 600,000 light years or more in some directions. The dark matter halo reaches potentially over 2 million light years, fading gradually until it's impossible to distinguish from the cosmic background. All of this has been here all along. Andromeda didn't grow larger. We grew more capable of seeing it. Each improvement in our telescopes revealed another layer. Each new technique exposed another component. The galaxy was always this big. We just needed time to understand it. And perhaps that's the deepest lesson Andromeda teaches. The universe is larger than we think, more complex than we imagine, richer in detail than we can capture in any single observation. Every time we believe we've seen the whole picture, we discover we've only seen a fraction. But that's not discouraging. It's wonderful. It means there's always more to discover, always deeper to look, always new layers waiting to be revealed. Understanding doesn't converge to a final answer. It expands, layer by layer, each one adding depth to what came before. Andromeda is vast, not just in light years, though those numbers are staggering. Vast in history, carrying the memory of every merger, every accretion, every slow gravitational dance over billions of years. Vast in structure, layered from bright disk through faint halo into invisible dark matter. Vast in influence, shaping the motions of satellites and streams across millions of light years. And vast in mystery, because even now, with all we've learned, we're probably not seeing everything. Future observations will reveal more. Better instruments will detect fainter structures. New techniques will map the dark matter more precisely. Andromeda will continue to grow in our understanding. Not because it's changing, but because we're always at the edge of our ability to see. Always working with the best tools available while knowing that better tools will come. Always measuring what we can while acknowledging what we can't. That's the nature of astronomy. That's the nature of discovery. So let yourself rest now in the knowledge that Andromeda is out there. 2.5 million light years away. A trillion stars organized into spirals and halos and streams. Ancient stars carrying the history of mergers long past. Dark matter extending millions of light years. Invisible but essential, holding everything together. A galaxy so large it took us a century to even begin to comprehend it. So vast that our best measurements still carry uncertainty at the edges. So complex that multiple definitions of size all remain valid at once. And so patient that it waited billions of years for conscious beings to evolve on a small planet orbiting a small star, to look up, to wonder, and slowly, carefully, to measure. You are those conscious beings. You inherit the accumulated knowledge of generations of astronomers, each one seeing a bit more, understanding a bit deeper, passing forward what they learned. And you can rest peacefully knowing that the work continues. Tomorrow, someone will look at Andromeda with better instruments. They'll see something new. Understanding will expand another layer. But tonight, you can simply rest. The galaxy will still be there tomorrow, vast and patient and beautiful, waiting for the next discovery, waiting for the next question, waiting with the quiet confidence of something that has existed for over 10 billion years and will exist for billions more. Sleep well. Dream of galaxies that refuse to fit inside the lines we draw for them. Dream of boundaries that fade instead of stop. Dream of a universe generous enough to keep surprising us, layer after layer, discovery after discovery, forever larger than we imagined. But let's linger just a moment longer, because there's one more aspect of Andromeda's size worth exploring. how the very act of measurement has changed over time, how our tools have shaped our understanding, and how each generation of astronomers faced the same galaxy with entirely different capabilities. In the early 1900s, measuring Andromeda meant exposing photographic plates for hours, hoping to capture enough light to see its basic shape. The measurements were simple. How wide does the glow appear? Where does it fade into the background? Astronomers used rulers on glass plates, counting millimeters and converting them to angular sizes on the sky. These measurements were precise for what they were. The error bars were carefully calculated. The techniques were sound, but they could only measure what the plates could capture, and the plates could only capture the brightest regions. Everything else was invisible, not because it wasn't there, but because the technology couldn't reach it. By the mid-1900s, better photographic emulsions and larger telescopes extended the reach slightly. Astronomers could detect fainter stars, trace spiral arms farther out, map the disk with more detail. Andromeda grew in these measurements, not dramatically, but steadily. Each improvement in sensitivity revealed a bit more galaxy. Then came electronic detectors in the late 20th century. CCDs that could record light far more efficiently than photographic plates. Suddenly, exposures that once took all night could be accomplished in minutes. More importantly, these detectors were sensitive to much fainter light. The threshold of detectability dropped significantly. With CCDs, astronomers began finding stars well beyond the visible disk. The stellar halo started to emerge, at first as a hypothesis, then as scattered detections, finally as a mapped structure. Andromeda was growing again, not because the galaxy changed, but because the tools improved. Space-based observations added another leap. Above the atmosphere, telescopes could see with unprecedented clarity. Hubble's images revealed individual stars in Andromeda's outskirts with sharp precision. What had been a diffuse glow resolved into countable points. Each star could be measured, cataloged, used to trace the galaxy's extent. Let this progression comfort you as you drift. Knowledge doesn't leap forward in sudden revelations. It accumulates. Each tool builds on the last. Each generation sees a bit more than the one before. And together, across decades and centuries, understanding deepens. Wide-field surveys brought yet another perspective. Instead of staring at small regions in exquisite detail, these surveys scanned vast areas of sky, looking for patterns across enormous scales. They could find stellar streams that individual pointings would miss. They could map the halo systematically, building up a complete picture star by star. And motion measurements, using spectroscopy to detect how gas and stars move, added mass to the picture. These techniques revealed Andromeda's gravitational reach, showing that the galaxy extended far beyond where any stars could be counted. The dark matter halo emerged not from images, but from careful analysis of velocities and orbits. Each of these techniques measured something different. Photographic plates measured light. CCDs measured fainter light. Hubble measured individual stars. Wide-field surveys measured extent. Spectroscopy measured mass through motion. And together, they built a complete picture. Or at least, as complete as possible with current technology. Because here's the profound truth, we're still limited. Even our best instruments have thresholds. There are stars too faint to detect. Dark matter distributions too subtle to map precisely. Regions of Andromeda that remain below our current sensitivity. Future technology will reveal more. Just as Hubble revealed what photographic plates missed, future telescopes will reveal what Hubble misses. This means Andromeda's measured size will likely continue to change. Not wildly, not randomly, but gradually, as instruments improve. The disk is well characterized now, unlikely to grow much more. The stellar halo is mapped fairly completely, though fainter structures might still emerge. The dark matter halo remains the most uncertain, its exact extent still debated. But that uncertainty is not a flaw. It's honest. It's a recognition that we're working at the limits of what's possible. And those limits keep moving outward as technology advances. There's also something worth noting about how astronomers communicate these changes. When new measurements revise Andromeda's size, the language is careful. Not, we were wrong before, but new observations extend previous measurements. Not, the old data was bad, but improved sensitivity reveals additional structure. This careful language reflects a deep respect for the work that came before. Early astronomers weren't mistaken. They were working with the best tools available. Their measurements were valid within their limitations. Later work doesn't invalidate earlier work. It extends it. It adds context. It reveals what was always there but couldn't yet be seen. As you rest now, appreciate this collaborative nature of science. No single person measured Andromeda's size. Thousands of astronomers, across more than a century, each contributed observations. Some took the photographs. Others developed the techniques. Others built the telescopes. Others analyzed the data. And together, collectively, they revealed a galaxy far larger than any individual could have discovered alone. This is how knowledge grows. Not through individual genius, though that plays a part, but through accumulated effort. Each generation stands on the shoulders of the last, seeing a bit farther, understanding a bit deeper. And each generation knows that those who come after will see farther still. Andromeda also teaches something about the nature of boundaries. In everyday life, boundaries are often sharp. A wall ends. A border is crossed. A line is drawn. But in nature, especially at cosmic scales, boundaries are rarely so clean. The edge of Earth's atmosphere doesn't stop suddenly. It fades gradually, thinning until it blends imperceptibly with space. The edge of the solar system isn't a line. It's a region where the sun's influence gradually gives way to interstellar space. And the edge of Andromeda is the same. Not a wall, but a transition. Not a border, but a fading. This is true for the disk, which doesn't stop but fades as star density declines. It's true for the stellar halo, which thins gradually until individual stars become impossible to distinguish from background galaxies. And it's especially true for the dark matter halo, which decreases in density so slowly that defining an edge becomes almost arbitrary. In a sense, Andromeda doesn't have an edge. It has a gradient. A slow transition from definitely galaxy to maybe galaxy to probably not galaxy to definitely not galaxy. And where you draw the line depends on your definition, your sensitivity, your purpose. This might sound frustrating, like the universe is being deliberately unclear. But it's actually liberating. It means we don't need perfect precision. We can describe Andromeda's size as a range, as a collection of measurements, each valid for its purpose. The disk is this wide. The halo extends this far. The dark matter reaches approximately here. All true. All useful. None complete on their own. Let that ambiguity be soothing rather than unsettling. The universe doesn't demand that we know everything precisely. It allows for softness, for gradual transitions, for boundaries that blur. And in that allowance, there's room for continued discovery, for refinement, for the joy of finding something new. There's also profound beauty in how Andromeda connects to everything around it. The galaxy doesn't exist in isolation. It's part of the local group, a collection of dozens of galaxies bound by gravity. The Milky Way is its largest companion. But there are others too. M33, another spiral, smaller but still substantial. Dozens of dwarf galaxies, tiny by comparison, but gravitationally significant. All of these galaxies interact. Their dark matter halos overlap. Their gravitational influences blend. The space between them is not empty, but shared, shaped by multiple masses, responsive to multiple pulls. In this web of interaction, asking where Andromeda ends and the local group begins becomes genuinely difficult. Is a satellite galaxy on the edge of Andromeda's halo part of Andromeda? Or is it separate? If it's gravitationally bound, does it count as part of the system? What about stellar streams that extend into the space between galaxies? Do they belong to Andromeda or to the local group as a whole? These questions don't have simple answers. And that's okay. The universe is complex. Galaxies are not isolated objects, but participants in larger structures. Their boundaries overlap. Their influences intertwine. Andromeda is both a galaxy and a node in a network, both a distinct structure and part of something larger. As sleep deepens fully now, hold this final image. Andromeda as a vast, layered system. Bright spiral arms at the center, surrounded by a dimmer disk. That disk embedded in a sparse stellar halo of ancient stars. The stellar halo floating within an enormous dark matter halo. And all of it interacting with the Milky Way's similar structure. The two giant galaxies approaching slowly, their halos already intermingled. This is not a simple object. It's a cosmos unto itself. A trillion stars, each with its own story. Stellar streams marking ancient mergers. Satellite galaxies slowly spiraling inward. Dark matter providing invisible scaffolding. All of it held together by gravity, organized by billions of years of evolution, extending across millions of light years. And all of it, every last bit, was hiding in that small smudge of light early observers saw. The galaxy was always this large. We just needed time, technology, and patience to see it properly. That's the final lesson. The universe is generous with its secrets. It doesn't hide them deliberately. It simply exists on scales and in ways that require effort to perceive. And when we make that effort, when we build better tools and ask better questions, the universe responds. It reveals more. It shows us layers we didn't know existed. It grows larger not because it changed, but because we learned to see. Andromeda is vast, larger than early astronomers imagined, larger than most people realize, large enough that we spend a century discovering its true extent, and we're probably still not seeing everything. But that vastness doesn't make it incomprehensible. It makes it worthy of study, worthy of wonder, worthy of the patient, collective effort of generations of astronomers. And now you can rest completely. The galaxy is out there, vast and patient. It will be there tomorrow, unchanged by our measurements, indifferent to our wonder, simply existing as it has for over 10 billion years. A structure so large it challenges comprehension, so beautiful it inspires awe, so patient it waited billions of years for beings like us to evolve and look up and slowly, carefully, begin to understand. You are part of that understanding. You carry the knowledge that Andromeda is not small, not simple, not easily defined. You know it's a layered system extending millions of light years. You know it grew through mergers and continues growing still. You know most of its mass is invisible. You know its edges fade rather than stop. And you know that future observers will see even more, will measure more precisely, will extend our understanding farther still. That's not a limitation. That's the beauty of it. The universe always has more to teach, always has deeper layers to reveal, always rewards those patient enough to look carefully. Sleep now. Dream peacefully. Let thoughts of vast galaxies fade gently into the background. Let the numbers dissolve. Let the measurements blur. All that remains is wonder. Simple, quiet wonder at a universe so much larger than we can easily imagine, yet knowable through patient observation and careful thought. Andromeda is out there. Vast, beautiful, patient. And that's enough. Good night.